Right, okay. So before we get started, let's just talk a little bit about the assignment 9, which was just due, and then assignment 10, which I just put up last night. And then hopefully we'll be able to talk about assignment 11 soon. It's done being written as far as the code, so it should be up soon. I just need to get somebody to proofread it, and then I think we're okay. But anyways, so assignment 9, let's just go over the write-up really quick, and then we'll take a look at assignment 10. So the first question was explain what a base case and a reduction operator are, and why are those needed to do something recursively. So a base case, right, that's kind of like a stopping point. It's the point at which we have like a definition for our base case, or for our problem, right? So if I was to use the example of factorial, then by definition we have 0 factorial is 1, right? So that's our base case. And we could use something else as a base case, like 1 factorial, or we could have multiple base cases and say, if we wanted 1 factorial is equal to 1, and use these both as base cases. But the idea is that we at least have one base case, and we have a sufficient amount that we can cover all of the stopping points that we want. So it's like a stopping point or a starting point usually in the context of math. And then a reduction operation, right, was just a operation to have us approach that. So in factorial, we said n factorial was defined as n times n minus 1 recursively factorial, and so n minus 1 factorial is already defined if we're at n factorial because it's less than it, and we know that subtracting by 1 is a reduction operation, right? So reduction is just having it approach the base case. So if I had 5 factorial, then using this definition, then we know it's n, which is 5 if we're taking 5 factorial, times n minus 1, which is 4 factorial, but we'll just leave it as 5 minus 1. And this is the reduction, right, is that it makes it into 4 factorial, and 4 factorial is a smaller number. And so if we kept applying that to 4 factorial, 3 factorial, 2 factorial, we would eventually reach the base case, which is what we want and what a reduction operation should do, right? And then just, the thing to remember is that it's not always strictly something like subtraction or division. In the context of the program, right, that you just wrote, assignment 9, the reduction operation was opening a doll inside of the current one. And the idea there was if you take any stack of dolls and you open the one inside of it. So if this was my stack of dolls and this was the outside one, then if I try to open this one, ignoring the one on the outside, then this is a stack of dolls, right? This group of 2 is also a stack of dolls, and it's one that's one smaller than the one we started with. Therefore, we're reducing it if we open the inner doll. Right, so I think that answers question 1. Question 2 was, is it possible to replace any loop, that being like while or for loops in C++ with recursion? Explain why or why not. And the answer to that was yes, and we did it in one class. There's a function I wrote somewhere on Canvas that shows that you can do that. And it definitely is possible, right? We could just replace whatever the thing is we want to change over the loop, and have that be our parameter that we reduced in some way. So totally possible, and if you're a computer science major, you will learn about languages that only use recursion and don't support loops, like Lisp or Scheme or what have you. Probably in like 326. So there are languages that don't use loops at all, and they use recursion instead. So definitely possible. And then last part we had, I think, no more questions after that, is below is some code to find the factorial of some integer n. Explain what is wrong with code and how to fix it. And so the thing that was wrong with this one was the fact that it has no base case. So this just recurses forever. It calls factorial of n minus 1, so it does a reduction operator, but it's not reducing towards anything in particular because there's no base case. So it'll never stop. It'll just stack overflow. So just remember, we need some sort of base case and some sort of reduction operation, and they don't have to be super rigid in the way you do them, you can kind of be free about it, and maybe have some interesting cases if your problem is, I guess, complex, sophisticated. I'm not sure what the word would be for it, but in the case of like a doll, maybe it wasn't obvious what the base case was all the time. Right. Any questions on any of those? So move over to assignment 10 then. I guess you should probably zoom in so it's readable. So I put this up on Canvas last night. It's basically a linked list. Well, it is a linked list, and we just have a special name for it. So imagine you're making a train. So a train has those compartments, right? Those cars, and they kind of all link together, right? So you can imagine it's kind of like a linked list. So here we're going to be making a train, and it's basically just a linked list with 2 data fields instead of 1, which is not. It doesn't really change how we do the linked list, right? The data field isn't the part that we use to traverse, so it won't change too much. So we're going to do 2 things essentially to this linked list. We're going to sort it in 2 different ways, which is going to be bubble sort and insertion sort. And we haven't gone over insertion sort yet, partially because, like bubble sort, I don't think it's a great algorithm, so I didn't really cover it, but we'll talk about it now so that at least you have the idea, and then I'll try to post some code on Canvas so that you at least have that as a reference. But just consider we're going to be doing it a little bit differently because it is a linked list. So there will be 2 classes: the train, which is the train itself. So that's basically the linked list class. It's going to have a head pointer pointing to the compartment at the front, the wagon at the front, and then it's going to have some other information here. So it's going to have length, which just keeps track of how many things are actually in the list itself, and I think that'll be helpful for sorting. There's display, which will just print all of the nodes, so you'll just need to follow the next pointers until you hit the end, and then print all of them, and we'll get into what it means to print it in a moment. You'll have a constructor with an integer, which is just how many wagons that the train will contain. The destructor should deallocate all of them, and then we have 2 sorting methods, which we'll talk about in a little bit, and then 2 other functions, swap and compare. So compare is essentially just a greater than operator. It's kind of like the is bigger from the last assignment, and then the swap is, it swaps them, right? So that's like the bubble sort swap that we've gone over. So I'm pretty sure most of you know how to write that at this point, right? So I won't talk about it too much. And then compare, I guess you do have the option to do it in any way you want. I guess, okay, so he has it as kind of like the normal compare integer return. I'll talk about that in a moment. Some languages support a comparison function, and I kind of have it built into a class they have. So I'll try to explain that in a second. Right, and so the other part would be the wagon, which is like the node here, and the data fields are a string for the company that owns that specific wagon, and then an integer for how many pounds or kilograms or whatever that it's holding. And then it has a pointer to the next wagon, so it's really just a node from a linked list, right? And then we have a brief explanation of these parts, but we just talked about that there. So what you're going to need to do is essentially read in this input file, and I don't mind if you do it with either a command line argument or if you just hard code the name of the file. I'm okay with either. Honestly, if you want to hard code it, I think that's probably easier for me to debug too, so that might be good. So something actually I guess I should address before we go too much further is the fact that this one's a bit more open-ended. So you'll see I did at least write a little bit more for you. That main is really just a skeleton in terms of describing what you need to do. So this one's a bit more open-ended. as long as you have some sort of way to do this, then that's okay. So there's really not a whole lot of code for you. It's pretty much just these comments and the headers that I added for the sake of helping you organize it a little bit. Yeah, so you're going to have to actually write, which is maybe some good practice here, to actually have you write your whole program from scratch. That way you're kind of used to it. Hopefully this won't be too bad, because there's really, I think the meat of the program is these two. So you're going to need to read this input file and then create a train from it. So we have this input file, and it's included on Canvas as well, so I'm just going to read it from here. We have 3 numbers at the start of the file. So the first one is the number of companies that you're going to expect to read in. So these are the companies that can own a train: Freightliner, Amtrak, Metrolink, and Union Pacific. So in the context of the program, the wagon has a company that owns it, and then an amount of pounds or whatever weight that it holds, or blocks of information or whatever. So you'll need to give it one of those company names and then a integer for the amount of stuff that it holds. And then we have, after that, this will be the minimum weight that a train wagon can hold, and this will be the maximum weight. So we'll need to maybe talk about random number generation, if anything. But if you want to just do it in a systemic way where you just start at 10 and go to 100 and then wrap around, I'm okay with that too, honestly. But maybe we'll just talk about random generation again, because I think you talk about that in 135, right? But just as a reminder, I'll actually have to look up. I think it's in C Standard Library and C++, but we'll double check. Right, so you'll have those 3 numbers to read at the very beginning. You can store them in a variable that reads how many trains there are, and then the minimum and the maximum, and then store these in a vector of some kind. And then this down here I think is just a little bit more of an explanation. So we'll come back down to there in a moment. So the only other comments I think I had were on compare and then the constructor. So the constructor is going to take an integer which represents how many wagons the train is going to have, and you're going to need to read that number from the user. So you'll need to prompt and then cin and then construct a train. And so it'll need to create all of those wagons, insert them in. So remember that means that we follow the head pointer until we reach the end, and then insert it. And then it will randomize the company and the load. So we'll have 4 companies here, but you'll need to randomly pick a string from your string vector. Again, I recommend just using a vector for all of this, all of these things, because I think it's useful. And then you will need to randomly generate a weight of the load in tons, apparently. Right, so maybe we should talk about the random number generation in a moment, and then we'll address selection sort. But before that, the other part was compare, which is basically like greater than or less than. The way that works in a lot of languages is if you call a compare function, rather than be like greater than or less than, it will actually tell you which one it is, regardless. So if I compare this wagon to that wagon, it will return a negative number. Usually I just say -1. So return -1 if the first object is less than the second object. Return 0 if they're equal, and return a positive number. So I usually say +1 if the second number is greater than the first number. So just for an example, if I was to compare 2 integers, we'll just say I0 and I1. Then the way I would do it is if I0 is less than I1, return a negative, basically telling that the first one is less than the second one, and then else if I0 is equal to I1 return 0, and else return 1. Usually the way I do it, but it's basically just a way to do a comparison function, so like greater than or less than, but it addresses all three cases of being strictly less than, equal to, or strictly greater than. It covers all three, which you can't do normally, right? Because if you do less than or greater than, then the opposite includes equal, and vice versa. If you do less than or equal, the opposite includes the one without the equal. So it's just a helpful function that you can use. And so what I suggest doing here when you actually write this one is, I assume the way it's intended is to compare, when you compare the two wagons, is to compare the loads of the two. So if the load of the first one is less than the load of the second one, then return a negative number. If they're equal loads, then return 0. And if they're greater, the one on the left is greater than the one on the right for the loads, then return a positive number like 1. So pretty much it would be this exact code, but using the loads instead of these random integers that I gave. Right, any questions so far before I go on to the next part? Actually, let me look up where the random numbers are in C++. I think it's C standard library. Yeah. Maybe I'll modify, actually, I'll maybe add that to the skeleton and upload it to Canvas. That way you all have a bit more to work with. So let's just mention that really quick, at least so that you have it for the future. And I'm sure most of you have done this in 135 anyways. So we just need to include C standard library. This is the library that, C standard library, it's the library that the random number generator is in. And then I would also maybe recommend including time.h. But I guess that's not always necessary. Depends on how you want to seed the random library. So remember that there is a function called srand which seeds the random number generation. Basically, if you provide this a number and you always use the same number, you'll always get the same random numbers when you go to generate them. So the idea here is that we want to seed it maybe differently every single time, which is where I usually use time h. So I think the function, and again, I'll update the skeleton and maybe just give this to you, is time null, and then that should seed the random number generation based off of the time that you're running the program at, which will make the numbers actually seem a bit more random. And then the way we get random numbers, right, is we just call rand, and it gives us something. So remember, the way we get a maximum is we just mod by the maximum, and right, that will always keep it less than. And just I guess if we want to consider, and we'll try to do this really quick so we don't spend too much time on it, if I have a min and a max range, in fact, I'll probably just add this function for you. If we have a min and a max, so in this case, in that file, the min was 10 and the max was 100, right? Then the way we want to generate a random number between these is, so the maximum is going to be 100. We want to rand mod, and so I actually just do it by the range between these two things, max minus min. So in this case, that would be 90. And so what this will do is generate a random number between 0 and 90, right? Because modulus always goes from 0 to 89, actually, I guess. So I guess it depends if we want this to be inclusive. We'll just say no. So this will generate a number between 0 and 90. In other words, between this starting number and the ending number in terms of like the length of between them. And then if we know that's between 0 and 90, then we can always add the min to it, and that will shift it over by 10, right? So if this is 10 in that case, then now the numbers that we get are 10 plus 0, which is 10, and 10 plus 90 as the greatest, which is 100. And so we cover that whole range, right? I'll probably just write a function for you when I get a moment today that just does this for you. But it's always good to know how to do, right? I mean, even outside of the scope of this class, maybe good to have. I apologize if I'm kind of just waving my hand and being like, the math is magic and works, but I just don't want to spend too much time on it. Right. So I think, again, any questions on this so far before I move on to the last part of this assignment? If you have any, just feel free to interrupt me. Okay, so you're going to need to implement two sorting algorithms, bubble sort, which I'm sure you all are pretty familiar with at this point, since we ask you to do it almost like every other assignment, it feels like, right? So I'm going to assume everybody knows how to do bubble sort. Insertion sort, they maybe talked about in 135, not super sure, and I know I definitely haven't brought it up. So let's talk about that. I guess I technically kind of have, but let's address it by name and maybe talk about the philosophy behind it. And then I'll post the code for you later. So let's just, for the sake of time, not actually code it up, but at least talk about how it works. So let's say I have a list and I want to sort it, and it has 2, 4, 3, maybe it would help if I didn't have the smallest first. So let's say 7, 3, 4, and then 2. So the way selection sort works is it's similar to bubble sort in that I would do 2 for loops. So for I is 0 to length, and then another inner loop where it's for j is 0 to, well, actually, that's not true. I'd probably use a while loop for the inside if I was coding this one. While not in place, we'll just say whatever you want that to mean. But we'll address what it means. So I'd have one for loop, and so kind of like bubble sort, there's a for loop that always goes and represents how many things are sorted, right? So in bubble sort, the outer loop represents how many things at the end of the list have been sorted already. And so the size of our list kind of shrinks over time as we approach length many things being sorted. Same sort of thing here. We're going to sort them, we're just going to do it in a bit of a different way. So the way this works is we start with whatever the I is. So we'll basically move from left to right and then move things as far left as they need to go. So when I start here with 7, I'm basically going to say, is there anything to the left that is smaller? And the answer when you start a list is always going to be no, because there's nothing to the left. Okay, so that doesn't change anything. So after the first iteration, we would end up with just the same list. So really, you could start at I equals 1 if you wanted to. And then we go and we look at the next thing. So here, we say 3. Is anything to the left of this smaller? And it is, right? So there's 7. So what we'll do is we will swap them. Until we get to a point where that's no longer true. So I'll use blue here to mark the things that have been sorted. So if I move 3 to the left, then it is sorted up to at least this point, right? And as we go, we'll end up sorting the rest of the list. So unlike bubble sort, where it sorts the right side ends up being sorted, the left side ends up being sorted here. Right, so that 3 now, there's nothing smaller than it to the left of it. Or sorry, there's nothing smaller than it to the left of it anymore. Yeah, right. So if we go to the next part, we would have to look at the next number in the line. So we looked at the first position, then the second position, and the third position. We're going to go until we reach the thing. And so what we want to do is we want to move 4 to the left as long as there's something smaller than it. So here, 7 is smaller than 4, or sorry, 7 is bigger than 4, right? I think I made a typo here. Is anything to the left that is smaller? Whoops, not. Sorry. So if the thing to the left of it is not smaller, then we need to move it down. So it's almost like the opposite of bubble sort, right? Where if something is greater than the thing on the right-hand side, then we swap it so that the bigger thing's on the right. Here, if the thing on the left-hand side is bigger, then we move it to the right as well. Which I guess is almost the same thing, it's just going the opposite direction. Right, so we would see that 4 is smaller than 7, so what we do is we move the 4 over. And then we would go and we would check again. So first the 4 looks at the 7, sees that it's not smaller, and then it goes and it checks the 3, and it sees that it is smaller. The 3 is smaller than the 4, that is. So at that point, we're done, which means that 4 is in its right place. And so the last thing we would need to do is go and compare the last number, which is the 2. And so you'll see that the 2 we need to do the same sort of thing where we check as far as the things to the left of it, is this smaller than it? So is 2 less than 7? Yes. So we'll move it to there. And then we'll check, is 2 less than 4? So it is, so we'll swap it with that. And then we'll need to check, is 2 less than 3? And it is, so we'll swap it with that. And so by the time we finish, we should end up with an entirely sorted list. And this might be a little bit hard to visualize in terms of me just writing it on a whiteboard. So maybe I'll try and find maybe something that gives a better visual for this and post it on Canvas for you all. Just 2, I guess, closing things about this. The idea here is that we move every element to its correct place in the list to the left of it. So if we kind of restarted and looked at this, we started with 7, and what we wanted to do is we want to put it in the correct place as far as the list up to that point. By definition, if you have one thing, that's already true. When we move on to the second one, what we want to do is put the 3 in its right place in the list to the left of it. And the list to the left of it is just the 7, in which case the correct order would be 3 and 7. So it's almost like ignoring everything that's not up to this point yet that we're checking at. Make sure that the list is sorted and make sure that we move the thing to the right place. And the way I've heard it described, kind of just as an intuitive way, is it's like using a deck of playing cards. So if I gave you in the same order that we had here, the 7, 3, 4, and 2. So if I gave you, let's just say, the 7 of spades, and then I think it was 3, and then 4, and then 2, and then the 3 of spades, and then the 4 of spades, and then the 2 of spades, in terms of how you would put that in your hand if you were playing like poker or something like that. Then if I give you the first card, you would just be holding it. There's not really anything special about that, right? If I give you the second card and I put it, and you always, let's just say, for the sake of consistency, put it at the right side of your deck. The way you would kind of want to organize this is most people, I think, put their cards in order, right? So the way you would organize this is you would shift the 3 over here and move it, and then, that would be your hand of cards now, right? And then if I fed you the next card, the 4, then you would say, oh, well, that's not in order anymore. I need to shuffle that over, right? And so you'd get 3, 4, and then 7. And then if I gave you the 2 to hold in your hand and you put it at the end here, then you would kind of shuffle it all the way through, right? You'd shuffle it down here and then down there and then to the left until your cards are in order again. So the idea is that we keep adding new numbers further and further into the list, kind of as like a card in your deck, and we insert it into the deck in the right position that it needs to be, basically by moving it left until we know it's in the right place. And again, I'll maybe try to post something that gives a better visualization. I apologize if it's a little hard to draw here, but hopefully you get the idea. Any questions before I move on from that, though? Not for me? Okay, fair enough. If anybody does have questions later, let me know. I apologize again if I'm just kind of waving my hands and saying this is how sorting works. I wasn't expecting to have to factor this in so soon. Right, okay. Fair enough. But if you do have questions, just stop me. Okay, so last thing about assignment 10, and then we'll move on to talking about, stuff again, is... Oh, actually, no, I should mention one more thing about the linked list. So just consider, you're going to have a swap function, and you're going to need that for both bubble sort and insertion sort, right? So there's a wagon 1 and a wagon 2, let's just say W0 and W1. W1. Then, because it's a linked list, the whole swapping thing might end up being a little bit different. So consider if we have this node like this, and then we have this here, and let's just say we want to swap, I don't know, this one and that one. What we'll need to do is, well, this function only takes 2, right? I suppose what we can do is we can actually just swap them using the pointers. I think that's the best way. That's just kind of strange to me that it's using 2. So yeah, I guess we're gonna need pointers regardless. So it's not an array, right? So we can't just swap directly, but I think we might be able to get away with it. So let's just say we have this first one, so that's W0 is that pointer, and W1 is the blue pointer. So we can say we want this one, the one at W1 at the position W0. So I guess we'll probably need a temporary variable, right? That's how we typically do swap. This might actually just end up being the same. I just want to be safe. Let's just set that equal to W0. So now we have a pointer that points to that, which means we can move W0. We can set that equal to 1. Actually, I think this is fine. And then set W1 equal to temp. Never mind, I think I worried too much. I was just concerned about the pointer part. Yeah, that looks the same, right? Okay, never mind. No big deal. I think swapping in a linked list shouldn't be that big of a deal, right? we should be able to just swap that way. I guess the thing is, if we swap it this way with the pointers, then the fact that this points to here should actually be all right, because we're going to swap these two things and their locations. Oh wait, but this is not going to point to the right place anymore, right? Because it was pointing to this previously. So we actually do need to do something different here. So notice if I swap these, everything on the outside is still going to be pointing to the right place, but if I swap these, right, then the things that we're not swapping should be still okay, I suppose. But if I swap the blue one into this position, then now its pointer is pointing to null, and this one is pointing to... Oh, actually, yeah, it's pointing to right here, right? It's pointing to the one that used to be in front of it. So this is the blue one, and this is the red one. Okay, so my worries were founded. We actually, there's a problem we need to address. So we need to update these two pointers that we swapped. So we'll need to point this one But if they're next to each other, we have an issue. I'll just point back to itself. And this is a bit of a problem. If they were separate, this would be easy. Yeah, so we're going to need to address two cases. So let's just throw that off to the side here. We'll say that this belongs in there. So if either one were swapping, if W0, the next pointer for that, is equal to W1, or the opposite is the case. So if either points to the other one, then we have to do something special. Actually, I guess we should separate these. So if W0 next is W1, which is what we had originally here, right? If they're next to each other, then we're going to have to do something special. So what I'm going to need to do is make this point to here and make that point to the same thing that it was. So this is the W0, right, the red one. So we need to say that W0, that one's next is W1's old next. Right, so what that says is make this pointer the same as that pointer. So that would sever this, right? And copy it so it would point to there. So in other words, it'll point to the thing after it, and then we need to address this pointing to there. So that would be the next of W1 we update, so we can overwrite that one. To be W0. The only reason I say this one should be special is because of the fact that it's going to end up pointing to itself if we do it the normal way, which we'll get to in a moment. But hopefully this is clear. So what we're saying here, right, is if the two things are next to each other, specifically in the order we had, is so if the W0 next, so if this one is pointing to the other one that we want to swap it with, then what we'll need to do is set this one to point where the one that it swapped with used to point to, and then update this to now point to there, right? And so that should fix that problem. Really quick, let's talk about the other possible scenario, which would be that they're not linked together. So if I had this here, and let's just say I wanted to swap two that aren't next to each other. So if I wanted to swap this one and that one, actually now that I think about it, we're only really going to be swapping things that are next to each other in bubble sort and insertion sort. So this is probably enough, but let's just at least talk about it for a moment. Right, so if we want to swap these two things out, then if I swap that, then this one's going to still be pointing to null if we move it over here, and this one is going to still be pointing to the one before. It was pointing here. So I think after swapping normally, what we would need to do, right, is just make it so that this now points to what this was pointing to, and that this now points to what the other one was pointing to. So we just need to swap the pointers if that's the case, right? So this is a bit messy. I apologize. So else we would swap the pointers. So that one I think is pretty self-explanatory. So we would say wagon pointer temp. We'll just say temp2 because we used the name temp before, equals W0 next. And then W0 next is W1's next. And then W1's next is temp. So that one's just a typical swap. Right, okay, so that should cover it. So we really just needed a special case, because if we swapped it like normal on this one here, then just consider that this would have made itself point there, because, well, it's kind of a mess now, but this was originally pointing there, and this was originally, or this was originally pointing there, and that was originally pointing there. So if I swapped the pointers, it actually would have made it point to itself, which would have been bad. So if they're adjacent, we need to do that check. Just for the sake of the notes, the other check you'll need to do is else if W1 next is W0. Do the same as this, but backwards. And this is really clean code, right? But does that at least make sense to the line of thinking that if we swap two things next to each other, we kind of have a problem because it's going to double back and point to itself. It did here. But I guess I've kind of written the code for you, so I'll post this so you have it later. Any questions on that? I guess we've gotten quite sidetracked at this point. But I at least want to make sure everybody's clear on this so you don't have too many questions on it. Right. Okay. So last thing, for sure this time, for assignment 10, is the write-up. There are only 2 questions this time, and they're, again, a little bit open-ended. The first one is, what were your operation times for linked lists of size 100 and 100,000? So you can either, I'm not expecting like a super accurate time result on this, so either just run a stopwatch while the program is running, or if it takes a long time to run, which it might for 100,000, that doesn't actually sound too terrible, but it might take a little bit, maybe like 20-30 seconds. Then there's also a command in Linux just called time. So if you type time and then the name of the command that you want, so if I just did like time and then /a.out, it will tell you how long your program took to run. Now, just consider that does include any sort of time that it takes you to type in input. So we're probably not going to get something very accurate. In fact, I think it'll almost always take you longer to type than it will to do the calculation. So, that's not great. But maybe that'll help a little bit if you want to keep that. So you can use that in general if you just use the word time. It'll tell you. And I put this on Canvas as well, so that you have it. So just time that for the write-up. Give me something that sounds fair. It's not super important if your timing is not, ridiculously accurate to the millisecond or whatever. That's all right. And the second part was, are there cases in which bubble sort is a good choice? So you've probably been told that bubble sort is not a good sorting algorithm, and really it's not most of the time. So is there a case in which bubble sort is a good choice? And I'll let you think about that a little bit, but the hint I'll give you is consider the version of bubble sort we did at the beginning of the semester, and that you probably did in 135, where you use that Boolean is sorted, and it maybe helps you break a little bit early. So I'll give you the hint. When would that help? So in other words, when can you break early from bubble sort? And that would probably be the answer that you're looking for. So that would be the cases in which bubble sort is good. All right. Any last questions on that? That took me a really long time to talk about, apparently. But this program is quite open-ended, so I think maybe the time we spent is hopefully helpful. Okay. I'm just going to erase this. Right, one last thing before we get back to stacks and queues, and maybe I'll post it on Canvas too. So next week is study week. We have 2 days next week, and I'm going to try not to talk about any new material if I can help it. Would you rather have 2 days of review, or 1 day of review and then 1 day where we just talk about something that won't be on the test? Because I know I brought that up before, that we could talk about extra topics, but I figured it might be good to ask, would you rather do more review instead, or would you rather talk about something optional? One review, one optional? Fair enough. I'll probably, I'll put a Canvas, because I figured we have like a third of the class. I'll put it on Canvas and then just, I guess, reply to it as well. Maybe that seems fair enough. Well, I guess we'll see what everybody else says too. Okay, fair enough. Yeah, I'll post that later. Right. Okay. Now let's talk about stacks. Last time we talked a little bit about... Really depends, actually. Okay, fair enough. If you feel like you needed the extra review, and I see that a fair amount of people, even if it's not the majority, I might still just do the review, in all honesty. Just because I guess it's probably more important to talk about this class, if that ends up being the case. Right, so last time we talked a little bit about stacks and queues, and at least the idea behind them. So a queue was kind of like how you would expect something to kind of be ordered. So if this was the top or the front, and then this was the top of a stack, and then bottom, and then the bottom here. And I wanted to insert some items, so I insert into both of them. So let's just say I insert A, then B, then C. Then what we said was a queue kind of goes how you expect it to. So when I insert an object into a queue, it always goes to the front of the queue, and that's the next thing I use. Whereas if I insert something to a stack, it goes to basically the end of it, and we put people in front of it, or objects in front of it, as we start to add them. So if I add in B to a queue, and kind of like a line in, a restaurant or, some public place, you typically get behind the person that you arrived after, and then you usually go after them, right? So in a queue, anything that arrives later will also be used later. Whereas in a stack, whenever anything appears, we put it at the top, or in other words, at the front of wherever it is we're doing. So if A arrived, then B arrived. B would be at the end of a queue, but at the beginning of a stack. And then if I inserted C, then C would go to the end of a queue and to the front of a stack, or the top of a stack. So that's just a bit of a reminder. Let's try to actually maybe implement these now, and we'll maybe just do it with a linked list. And so you'll see a queue is almost really just what we're used to. So let's add to the queue as we've been doing. We'll add A, and then we'll add B, and then we'll add C. I should probably do that in the opposite order. I don't like to put red and green next to each other in case anybody's colorblind. There we go. Right, so if we have a linked list, and we'll just say we have some sort of head pointer, which is going to be initialized to null, then if we wanted to insert A, what we would do is we would create a node, right, and then just make the head pointer point to it, and we would set its pointer equal to null, and that would be that. Right, so the insertion into this is called, for a queue, that's called onQueuing it. OnQueue, and then whatever it is that you want to onQueue. So here I've onQueued A by putting it into the list, and then if I wanted to onQueue B, I would just basically do it the way we have been doing. I would follow all the nodes until I reach the end, and then now B goes to here, and this would be null, and then when we insert C, we would make it point to the end, and we would insert it in, and then it would go to the end. Right, so onQueuing, if we use a linked list, basically just the same exact sort of strategy that we're used to for insertion. Just put the thing at the end, and then that's all we really need to do. So onQueuing, at least in a linked list, really not different than what we've been doing. Now, the removal is going to be a little bit different. So, I guess we could say this is a lookup almost, but it's taking something out of the queue. So, in a case of like standing in a line, then dequeuing would be, the cashier asks for who's next, and then, the person at the front of the line walks up. So here, we would want to dequeue A, then dequeue B, then dequeue C. So that'd be the order that we take these things out of the queue, right, is the order that they arrived in. So again, this was like a first in, first out sort of deal. Right, so when we dequeue from a queue, so let's redraw this down here so that we can work with it. What we're going to want to do is we're going to want to remove the head, right? The head is going to be pointing to the first object in our queue, or first node, I guess. So as far as removal, dequeuing things, we'll want to make the head point to the next thing, and then, now that's broken, right? And then return this object. And then when we do the next one, we'll need to remove it, and then move the head, and then take it out, and then so on and so forth, until we end up with an empty queue. So if we just think about that really quick, what we need to do is we need to set the head equal to the thing that's next. So the head is going to be equal to the next thing, that the current head is pointing to, and then we would just return that head that we used to have. Now, we're kind of shifting things around here, so we'll need a temp variable. So we'll say that we need a node pointer that points to the old head. We'll just call it temp, I guess. Make that equal to the head, and then return the head. Now the only other thing that we'll need to check here is if the list is empty, we can't really remove anything from it, right? So what I would say is just, if you're going to implement this, that we make sure that the head is not null, because if that's the case, then we can't really remove anything, right? And that should be about it. And just to make sure that we always return a value, then we'll return null if that was null. Okay, so that would be about it for onqueuing and dequeuing. So queues, I think, are actually pretty straightforward. I think they're kind of common sense in terms of how they work. You know, the first thing that shows up is the first thing that leaves. And the insertion is really just what we're used to, and the removal is just always remove the head and then just update it to be the next thing. Now, queues are pretty useful, as you might imagine. You can use these for anything that you expect where the first thing that arrives is going to be the first thing that's out. So if you wanted to, let's just say, display messages as they come in, you would probably put them into a queue and then gradually dequeue them as you want to display them. If you had a system where you want people to wait their turns, then you might put them into a queue and then dequeue them as they go. Really, I think you probably get the idea as far as that goes, right? Now, a stack might not be as obvious, and it's probably not something that you might inherently think to use in your everyday life, but it really is very useful. So a stack, and we'll insert that in the order that we did the last one in. So we'll do ABC, and then we said that this, rather than being a first in, first out, is a first in, last out sort of deal. So as far as insertion goes, the initial insertion is basically the same. So if our head is null, then we just put it in to the list. There's not really anything special about that, right? So if I insert A, it would go into the list, right? There's nothing particularly strange about that. The next thing would be, though, when we go to push the next thing into the list. So rather than put it at the end, we want to put it at the beginning. So really the only difference between a stack and a queue in terms of their implementation, at least with a linked list, is that we want to put any new object at the front of the list rather than at the end of the list. In other words, the new object is going to need to become the head. So if I go to insert B here, what I will need to do is I'm going to need to set B to be the new head, and then I'm going to need to set B to point to the old head, which was A. So once I push in, it should look something like that. And by the time we're done, right, we'll end up having 3. Where the head of the list will be the last thing that we inserted, and the tail of the list will be the first thing we inserted. Right, so by the time I've added in A, B, and C, it will look like this. So this insertion, just as a reminder, we call this pushing into the stack. That's a push. And the removal is a pop. And you'll notice if we set it up this way that the removal is the same as the dequeue. So I'm not going to write it any different. But really what we would need to do, right, is just this exact same code. We would need to remove the head, set the head equal to the next one, and then return the value of it. In fact, I would probably return head data, not just head, but that's okay. And then return null if there was nothing. So removal is exactly the same. The only difference here is that we insert at the beginning of the list versus the end of the list. Right, so if we code that up really quick, what we're saying is we need to make a new node, set it equal to the head, and then make the old head equal to that part. So, right, I don't think we need a temp variable for that. We can just say we want to make a new node pointer, new node, however you decide to instantiate that. And then we need to make that new node, it's going to point to the old head, right? Because if we're inserting it at the beginning, then the old head is always going to be the next one that it is going to use. So we'll set it equal to the head, and then we'll make it the head itself. So we'll say head is equal to next node. And so this would be our push. Where you have some sort of variable that you're pushing into the thing. Really, I don't think that's that bad. There's not anything super complicated about that. The only thing which I didn't code here is just, make sure you're checking for if the list is null, then you put it into the list, right? Or at least you don't do this step, because then we wouldn't have that. Is that clear so far as the difference between those two things? So a stack, we put things at the beginning, and a queue, we put things at the end. And this is not a typical implementation of a stack, I would say, but it's what we're going to go with for now. Usually we'd actually put these all next to each other and then use a pointer, but that's okay. Okay. So then the usage of a stack maybe is not as obvious as the usage of a queue, since, again, I think that's something you encounter in real life a lot. Last time we talked a little bit about the most common use of it, which would be when you have function calls, because the most recent function you've called is always the first one that's going to return, right? There are some other uses as well, so let's just talk about maybe one that I feel like I encounter a fair amount. Are stacks used more in memory, such as pointer counters in assembly? For example, yes, you're actually... Are you taking assembly right now? That's actually exactly what that is. So when you do a program, right, if you wanted to, let's just say, store return values or store return addresses for your program, then you would put the return address on a stack, and then you would know it would go up, right? So you would do almost exactly the same thing, except rather than use the PC, because that is for executing instructions, right? The PC is the program counter, which tells you what line in memory that your line of code is that you're executing is on. You would use some sort of memory address for it. So if I had, and I apologize if this is a bit of a tangent, but we have a decent amount of time left, I guess. What you would do is the bottom object would go right here. So you would put that there, and then, so let's say this is like hex. So this is usually byte addressable, right? So this is hex 1, this is hex 0, this is hex 2. What you would do is you would push the thing onto there. So if it's an address, that's probably 8 bits, and then, 8 bytes, and then you would increment your pointer, whatever it is, so the memory address, by 8 every time. Yeah, so that's what you typically do a stack, is you just like you're saying there, you add by some fixed amount, being the number of bytes of the thing that's going into the stack, whether that be a return address for a function or variables for some sort of evaluation, which is actually how, like, when we write expressions in C++, like this, it actually pushes each of these onto the stack as it evaluates them, and then kind of you eventually work your way up. So in this case, if these were integers, it would add by 4 every time, since an integer is 4 bytes. Yeah, so that's exactly where that is. Yeah, and that's how you would do it in assembly or machine language. You would add by whatever amount that is. So the compiler actually basically writes it in machine code or assembly, or the code that it's compiling, that is. So when he goes to evaluate an integer, it will do that, and it will specifically add 4 bytes for an integer, or 1 byte for a character, or whatever it is. Yeah. So that'd be a very technical example, but that is a incredibly common example that you run into, is pushing memory addresses onto a stack specifically for function calls. Maybe a less tech-heavy example would be, imagine you're browsing the internet, and so you have your little window, right? Let's just say we have a browser, and it's not very good, but we'll put an E up there, and it looks something like this, right? So it has a forward and a back arrow. I guess what we're mostly concerned is with the back arrow, and then you can type whatever address it is. So if the first thing you went to was, let's just say, Google, what's going to happen is that's going to be the beginning of the stack that's going to get initialized. You should probably draw this at the bottom rather than at the top. So if you go to Google and then you type in something and you Google, computer science or something like that, and you get the query results and it shows you all of that stuff, and then you're like, oh, that's interesting, and you go to Wikipedia. And then you're done reading that, and you want to go and you hit the back arrow. What it's going to do is actually keep a stack of all of the pages that you've gone through. So it'll keep the Google page, and then the CS page, and then the Wikipedia page, and it will, once you hit the back arrow, it will pop. So this here, it's going to pop that from the stack, and then, if you notice, when you pop that from the stack, the new top of the stack is the page you were on before, right? So what happens when they do a navigation stack for stuff like that is at the top of the stack is the page that you're on. And so the more and more you hit the back button, the more and more it will pop from the stack until it gets back to the original page that you started on. And I guess another thing to notice about this is that if I was to go back to that Google search page and then click on the next link, let's just say, and it goes to like Stack Overflow, then that's going to take the place of where Wikipedia was, and now that's going to be the thing that we view. And again, we can always hit the back button on the top of the browser and get our way back. Right, so maybe that's another example of where we could use a stack, if that makes sense. And in mobile development, which is what I normally do, that happens as well on your phone, because when you open a new page, it will actually add it to a navigation stack that keeps track of all the pages. And whenever you hit the back button, if you have like an Android phone, if you hit the back button, it'll pop from that stack. So really, stacks are pretty useful. It's just maybe not as obvious as to where they're used. So let's go over one more example of where we could use that, and then I suppose we'll maybe call it a day. So let's say I had a string called hello, and I wanted to reverse it. because of the way a stack works, where the last thing is always the first thing, what I can actually do is push all of these onto a stack. So if I wanted to write a function, given that I have some sort of class stack, let's say string reverse. Equals that, I guess we'll say. What we can do is we can create a stack, and this is assuming somebody else has already written a stack class for you, which, you know, pretty much any language already is going to have that because of how common it is. Then what we can do is we can actually go ahead and push all of these things onto the stack. So I'll say for int I equals 0, I less than, we'll just say whatever the string is, we'll just say str string.length I++, and go and push all of those onto the stack. So we'll say s.push str sub I. So if I go in order and push these things onto the stack, let's think about what that looks like. If I had the word hello, and it was going to start at the beginning and push things on, so the first thing is obviously going to be the H, right? It's going to put that into the stack to initialize it, and then when we go to push the next thing, it's going to go above it, right? E. And then if I push the next thing, it's going to go above that, and if I push the next thing onto that, it's going to go there, and if I push another thing onto that, it's going to go O. Now, one thing that's maybe more clear here as I draw that is where it gets the name stack, is you're kind of stacking these things on top of each other until it becomes taller and taller. And the name overflow comes when the fact that it gets too tall. If you built a tower of blocks too tall, it's going to just start wobbling and fall over. Same sort of thing with that name, is because we put too many things on the stack, it just runs out of space and it breaks, and we can't use it anymore. And the name actually comes from, just a fun fact, name comes from going to a buffet. You know, if you go to a buffet, they have like those stacks of plates that they keep on a warmer. And if you try to take a plate that's at the bottom, you're just going to drop all of the plates and break it, and the staff's going to get angry at you. So, you usually take the plate off the top. But the way they put it into the stack of plates is they always put it on the top, right? So it's almost the same sort of thing. You pull the top plate off, and when you put plates back on, you put them back onto the top as well. So whoever invented stacks, I guess, was just hungry, or went to a buffet that day or whatever, because apparently that's where I was always told the name comes from. So, random fun fact. But anyways, this is the way the stack would look for that, right? We push H and then E and then L and then L and then O, and it works its way up. Now, if I went and I popped all of these, so I pushed it on, if I wanted to pop all of these off, what you might notice is at the top, the first thing that we're going to pop off is the O, and then the L, and then the L, and then the E, and then finally the H. So when we pop things, it's always in the reverse order that we push them in. So a common thing we can use that with is reversing some sort of order. We can push everything into a stack and then pop it all back off. And now that's assuming that we don't push anything extra in the meantime, and we just do one single push. So if I wanted to finish the code here, I would just say for I equals 0 to string.length, I can put into the reverse string, I can add the character that I get from popping it off. So plus equals s.pop. And oops, that should be there. And so this will do exactly what we just did in this picture. It will slowly take them off the top, and it will get them in the reverse order that we pushed them into. So we can get things in reverse if we put them onto a stack. In general, you want to use it if you want to keep some sort of history about something, or if you want to be able to roll backwards and revert some sort of thing that you've done. Okay, any last questions on that? Okay, sounds good. I guess I will see you all on Wednesday. We do actually have class. I think I made a mistake and put on the syllabus that we don't, but Thanksgiving is Thursday, not Wednesday, so we do still have class. I don't think we'll talk about too much, but yeah. I guess just let me know how assignment 10 goes, and I'll try to put a skeleton up when I get out of class today. Okay, fair enough. I will see you all on Wednesday.